Hi, everybody. Today, we are on to the limit definition of the derivative. We're in section 2.6, and we are revisiting the somewhat familiar image of having a function, f of x, that looks just like a parabola, so no big deal there. But remember that finding average velocity, we have been calculating that using the slope of secant lines, finding the y value corresponding to some number here, and then finding the y value corresponding to some other number over here. You get 2 points. You can find the slope between those 2 points, and that's an approximation of the instantaneous rate of change, at this point C. But we get closer and closer, we get better and better estimates of that actual instantaneous rate of change if we let the distance between this other point and C get close to 0. We have labeled this distance h in the past. You might also want to get used to referring to this as like delta x, because it's a change in x values. But really, that's just the distance between the 2 points that we're using to create the secant line. And the idea is if we get this closer and closer, we'll be able to make a tangent line. But remember, you can't create a slope from just using 1 point. And so we have to use this idea of a limit to approach a certain value for the slope, because we can't just use 1 point to make the slope. So the idea here is that we have a difference quotient. And again, this is rise over run. We've got y values over x values. And h in itself is kind of the difference between two x values, because it's the distance between two things. So we're now giving this a name. It's called the derivative. And it's noted using the prime symbol here. And we would read that as f prime of c. I've written down here a couple other alternative ways that you might see this written. Dy dx, df dx, or even just f prime. All of those are ways to denote we're looking for the derivative. And particularly, we're looking for the derivative, in this case, of some function f. So what we're doing here with this definition of the derivative is finding the slope of a tangent line at a certain point C. Later on, we're going to talk about a general derivative function, but this time we're just finding one specific slope at one specific point and corresponding to x equals c. So let's take a look at an example or two here. The first one is find the slope of the tangent line to this parabola at the point 2, 3. Then use this information to derive the equation of the tangent line. So we would be normally creating a sequence of secant lines that get closer and closer to what we want to aim for. In this case, instead of going straight to the graph, let's use the definition of the derivative and see what we get. So since we're focusing in on the point 2, 3, we're looking for f prime of 2, since that's the x value that we're putting in. And f prime of 2, according to our addition, is the limit as h goes to 0 of f of 2 plus h minus f of 2. That's the difference in the y values over the distance or difference in the x values, h. And then we would just continue. We would plug those things into f. So 2 plus h into f. That's kind of our first thing. And then we're subtracting off what happens when we plug 2 in for f. Still h on the bottom. Okay, let's multiply this first part out so that we get 4 plus 4h plus h squared minus 1. And now we've got 4 minus 1, so that's just going to be minus 3 over here in h. And notice that at this point, if we were to plug h in, you know, the terms with h would go to 0. So we would definitely have a 0 on the bottom. And if we put in 0 for h up here, we would have 4 minus 1, which is 3. And then we have 3 minus 3 on top, which is 0. We would be in an indeterminate form. So the stuff that we talked about on Thursday about evaluating limits is actually coming in handy right now. What we're going to want to do is cancel out a common factor of h on top and bottom. And we're going to be able to do that very soon. So like I said, the 4 minus 1 is actually a 3. And the 3 minus the 3 is going to be 0. So all we're left with is 4h plus h squared on top over h. And that allows us one more time. I know that it gets redundant to keep writing the limit as h approaches 0, but we do technically need to keep that coming along for the ride as long as we haven't evaluated the limit yet. So now we're able to cancel out a common factor of h on top and bottom. That gives us the limit as h goes to 0 of just what's left, 4 plus h. That's great because now when we plug in 0, we just get 4, and now we don't have to write limit anymore. And so hopefully the slope of the tangent line is actually 4 on this graph. And what we can do is, let's go ahead and open up GeoGebra and pull it up here. GeoGebra. Let's refresh it. Okay. Hey, we've got a tangent line. Remember, we are concerned with the point 2, 3. So that's where we're trying to make a tangent line. And I guess I have this already there. Big spoilers in terms of what the line actually is, but it does look like a slope of 4 makes sense. So far, so good. Let's go back to OneNote. Now, at this point, because f prime of 2 equals 4, we know that the slope of the line needs to be 4, but it does ask us to use this information to derive the equation of the tangent line. And the information we have now is a slope and a point. So we should use point slope form. For creating a line, and that is y minus a y value equals the slope times x minus an x value. And in this case, y value of our point is 3, the slope is 4, and the x value is 2. And we can just continue to work this out. 4x minus 8. And then y equals 4x. We add 3 to both sides and get minus 5. So that's how we got 4x minus 5 on the graph. Come on. There we go. Yeah, 4x minus 5. And it works beautifully there. Cool. So there's the limit definition of the derivative. at a certain point, we get one value out, and that's our slope. Point slope form is pretty handy. This is maybe a little bit of spoilers for what's coming, but I think it's good to know that in general, we're going to be able to make a tangent line, and I know that this is spoiling what's coming ahead, by using the derivative in the place of the slope and still having a, an x value and a y value. But let's say a tangent line at x equals c. So we've chosen c to be the point that we're building the tangent line off of. In that case, this becomes y minus f of c. The y value is just the function evaluated at c. The slope is f prime of c. And we have x minus c at the end. And if you want to get really fancy, we can change y into saying something like, oh, hey, this is the linear approximation. Maybe we, use L because it's a line. And then copy everything else down. But if we add f of c to both sides, we get a function form of the tangent line generally here. And yeah, this is really, really, really cool. And I'll show you how to program this into GeoGebra soon, so you can see a tangent line that just goes along the graph. It's like magic. It's great. Yeah, this linearization formula for coming up with a tangent line is derived from a point slope form that you've probably seen in an Algebra 1 class or Algebra 2. Cool. All right, so there we found the derivative using the limit definition. Moving on to example number 2. And yeah, I didn't erase example number 2 yet. If you want to take some time and write this down, you can. But the idea is really the same. Again, we are finding the derivative evaluated at a certain point. So we're finding d prime. Our function here is d prime of 2, because we're looking for the instantaneous velocity at t equals 2. Again, we're taking a limit as h goes to 0, y values on top, difference of x values on bottom. And I mean, even again, the reason I'm leaving this there is that it's another quadratic equation. This time it was x squared minus 1. This one is 5t minus 1/2 t squared. But the same kind of thing is going to happen. You're going to, plug in 2 plus h into this function. Then you're going to plug in 2 to the function. Reduce things down a little bit such that by this time you get to 10 minus 2 minus 8, and those are able to cancel, and you're just left with terms that have h on the top, and then you're able to divide through by h so that you have just 3 minus 1/2 h left over. And as you take the limit, as h goes to 0, you get 3. And so I guess this is, decent to look at again, because you kind of get a feel for what's going on overall. And yeah, if you want to pause the video and write stuff down, totally can. But pretty stinking similar to the one that we just did. And here again, we have a quadratic equation. We have the point in question. And I created this line using the slope that we found of 3. And we've got the x minus 2 part, and I added on f of 2, or sorry, d of 2 in this case, which is 8. And that shifts that line up so that it'll go perfectly through our point. So that part's looking good. That's example number 2. Example number 3, I've left blank, and honestly, I don't even really want to do it, but I left it there so to motivate the next part. Let's read it. A piece of rock is dropped from a height of 196 feet, and its height above ground level is given by this function. Again, a quadratic function. Where t is measured in seconds. Find the instantaneous velocity of the rock at t equals 1, at t equals 2, and t equals 2.5. And then, what's the velocity of impact? If you think I'm going to do the limit definition of the derivative at a point for t equals 1 and do this whole thing, and then t equals 2 and do this whole thing, and t equals 2.5, do this whole thing, and then figure out which t value will make sure that we impact, and then do the whole thing a 4th time, not going to happen. This whole business of evaluating the derivative at a point is pretty inefficient, especially if you want to figure out more than one slope at a couple different values. And so this motivates the derivative as a function. And instead of putting in a specific value of c, some x value where we want to find the derivative, here we just leave x as x. And we are able to get a formula for the derivative that will change depending on whatever x value we put in eventually. But it just means that we do the limit definition once, and we come up with a function that we're able to plug in multiple values into. So we're actually going to do it on the soccer ball. We're going to do it on example 4. Soccer player kicks the ball vertically upward so that its position relative to ground level is given by this height function. Find the velocity and speed of the soccer ball at t equals 1 second, 2.5, and 3.5, and then what's the ball speed on the impact upon its return. So my idea here is we're going to use the limit definition of the derivative, come up with a function for the derivative. But then, in order to come up with all of these different, slopes at different x values, what I would like to do is make the equation of a general tangent line, which, is not even really in this part of the book, but I feel like to make our lives easier, we should try doing this kind of a thing so that we can just plug in different values of c and get different tangent lines. It's going to be great. And I think that you can understand this. And if not, take a pause and you can dissect it a little bit. But that's the plan. We're going to use the limit definition of the derivative to find the derivative, and then plug that into the equation for a tangent line and be able to make them super fast. All right, so h of t. Ugh. H of t is not a great one when you're using the limit definition of the derivative, because you put h on the bottom and you take the limit as h goes to 0. So instead of h this time going to 0, let's use delta t. Like I hinted at earlier, I don't know, if you're looking at the difference between two t values, two time values, yeah, we can call this delta t, and that's functioning the same way that h has functioned, but well, now our function's named h. So yeah, I don't want to use that anymore. So we're going to take the limit delta t goes to 0. Okay, let's do this. H prime of t, so the derivative of h is equal to the limit as delta t goes to 0 of h of t plus delta t minus h of t all over delta t. And I know this new delta t thing is a little bit weird because you've got two symbols, but really that's just one thing. It stands for a difference of t values, and we're shrinking that difference of t values. So just treat it like it's one thing. We plug this in. This is going to be a little bit of a nightmare. We're plugging in t plus delta t everywhere where we see t up here. So we get minus 4.9 t plus delta t squared plus 19.6 times t plus delta t plus 1. That's the first thing. Then we're subtracting off, well, just h of t. Goodness. Okay, you guys can still see all that. Maybe here, I'm going to zoom in a little bit so that's easier to read. And let's scoot down so we have plenty of room to write. It's not going to be plenty. All right, that's the top. And then we got delta t on bottom. And goodness. We've got to multiply this first part out. So that we have, negative 4.9 t squared plus negative 9.8, because there's going to be two of these, t times delta t. And then plus delta t squared plus 19.6 t plus 19.6 delta t plus 1 and then minus all the rest. Actually, let's go ahead and write these as whatever sign they belong when we actually evaluate the subtraction. So we've got a plus 4.9 t squared and a minus 19.6 t and a minus 1. All over delta t. Now here is where we look through and use our eagle eyes to find out terms that will cancel out. So 4.9 t, those t squared terms cancel out. Let's find another one. Just 19.6 t. There's a positive version over here and a negative version over here, canceled. Also the ones, plus 1, minus 1. Those parts will cancel out. And notice those are all the terms that were in h of t. All of those cancel out. And all we're left with are terms that have delta t in them. So on the next time we can cancel out delta t on top and bottom. I'm going to use a purple. If we cancel out delta t, a delta t will leave this term. A delta t will leave this term so that we're just left with delta t instead of delta t squared. And a delta t will leave this term so that we're just left with 19.6 there as a constant. So in the next line, all that we're left with is the limit as delta t goes to 0 of negative 9.8 t plus delta t plus 19.6. And if we evaluate that limit and let delta t go to 0, all we're left with is negative 9.8 t plus 19.6. And so this is our final answer for h prime of t. We now have a function where, depending on whatever t value we want to plug in, we have a function that will give us the slope of the tangent line at that point. And what we're able to do now is, when we want to find the slope or, make a tangent line, let's zoom out just a little, scroll over, and then I'm going to erase this part to give us a little bit more room. If we want to find the tangent line, let me go ahead and write it in red like I did last time. We're going to take the derivative we're evaluated at a certain point that you're interested in. And we'll label that here. This will be at some c value, where t equals c. So at some t or some c. The derivative part would look like negative 9.8 times our c value plus 19.6. And that will give us our slope. Then we would have t minus whatever c value we choose, and we would add on h of c here. And actually, I'm reminded that we could have just abbreviated this as h prime of c, t minus c, and h of c. So that, yikes. I know that looks like a lot, but we're going to be able to make any tangent line using the derivative at a certain point, c, times t minus c, plus the y value, h of c. And that's going to be really great. So we click on this, and we have our parabola there. Notice that in GeoGebra, I can just type h prime using an apostrophe, and that does give us the derivative. In this case, it's giving it to us in terms of x, which is weird, but if you specify that you want t, it'll use t. Yeah, notice I've already done that. And so we have a function for h of, height. But now we have the derivative of, the position. And this function is actually the velocity at any given t value. This would be the velocity of the soccer ball in a vertical direction. So this line that goes down is actually the graph of the derivative function that we, won't examine too closely right now. But that's kind of cool. One of the things that, you do see it based on this is the initial velocity of the soccer ball, if we put in 0 for t, would mean that the initial velocity is 19.6 meters per second upwards, which is, kind of cool to realize. And then the velocity gets to 0 when it reaches the peak, and then the velocity becomes negative as it approaches the ground. So the velocity has changed direction and is now going down. So those are some cool things to look at with the velocity. But just for funsies, I took the derivative of the derivative. And when you if you think about what is causing the velocity of this soccer ball to change, it's gravity. And so gravity is the only thing that's accelerating this soccer ball or changing its velocity. And that happens to be, Earth's gravitational constant, 9.8 meters per second, is the acceleration function. So the fact that when we're doing these projectile motion problems, nope, wrong thing. One note, when we're doing these projectile motion problems where we have something flying through the air, it is not a coincidence that we keep coming up with quadratic functions. Quadratic functions are actually really good models of projectile motion, especially when you're not accounting for things like air resistance and stuff like that. It is a simplified model, but if the acceleration of the projectile is only being impacted by gravity, which, more or less when you're on Earth is a constant number, that shows up as the second derivative of the position function. So you've got position, then velocity, then acceleration. They're all related. Super cool. And I even went the extra mile here. Let's go ahead and get rid of the velocity and acceleration graphs, because which graph are we really here to see? The tangent line. And here, I actually made this new function. I guess I called it f of t. This is going to be the tangent line based off of the slope at a point. And for the specific point, I made c a slider so that we could change the value of it. That would be cool. So I'm just using what we did before, and take a look. I can just let that c value vary, and we get a tangent line that moves directly around the graph at any c value we want. That's awesome. And I guess, to make sure that we're looking at the point, I could add in the point c h of c to get that actual point of tangency there. But yeah. Nice. I love making dynamic things on GeoGebra. Anyways, what this allows us to do is to go back to the original problem and say, oh, if I want to find the velocity and speed of the soccer ball at 1 second, 2.5 seconds, 3.5 seconds, that's easy. all I need to do now is go back here and plug in 1. And yeah, for this, I mean, I guess you see it, it's really long here, but actually, I wonder if I show value. Ugh, it still shows it as expanded out like that. I bet if this was a function of x, GeoGebra would simplify all that stuff and you wouldn't have to read all the numbers. But I mean, the slope here would be whatever negative 9.8 plus 19.6 is. So that would be like 9.8. Oh, so the velocity here is still 9.8. And maybe that's what I could do. I could just use the function that I defined earlier. Yeah, v of c, the velocity, according to this derivative function, just 9.8. And very similarly for the other ones, we need to do 2.5 and 3.5 seconds. 2.5 up there. We're at negative 4.9 for that one. But again, we're just plugging 2.5 into the derivative function. That's cool. And then 3.5. That is an even more steep tangent line, corresponds to a slope of negative 14.7. Cool. Does this one want us to find the speed when it crashes into the ground? Yes. Speed of impact upon return, great. And again, in order to find that value of t, I mean, one way would be to factor the original polynomial, the original quadratic that we're given. Ugh. There's the root there, 4.05. So if we type in 4.05 here, I'm kind of reading there, but oh, see, that's not even perfect. Oh, actually it is, it's fine. If this thing had started off on the ground, then the initial velocity and the ending velocity would have the same magnitude, but they'd just be in opposite directions. So what I'm saying there is the initial velocity here was 19.6 going straight up. And if we had launched the soccer ball directly from the ground, the returning velocity would be 19.6 meters per second, just headed in a downward direction. But since we didn't start off at ground level, we started off 1 meter from the ground. The initial velocity that we have is actually just a little bit less than the ending velocity because there's still 1 more meter to accelerate than what we had to do up. So yeah, this number, negative 20.09, actually makes some good sense there. We had just a little bit more room to accelerate in a downward direction. Cool. All right. We did a lot with that one. A lot going on there, but we used the limit definition to find the derivative. We're using delta t there instead of h because h was already used here. Cool. And I made a note here on the next problem for me to use delta x because I hadn't gotten an opportunity to do that yet. And there's another cool video that I'd like you to watch that uses this kind of notation. This one actually, example number 5 here should genuinely be at least a little bit interesting, because we're not using another quadratic equation. Here we've actually got a square root function. I'll do this real quick, and then we'll leave this video probably to watch maybe right at the beginning of your activity. And we might need to think about that activity kind of being something that we work through together a little bit. We'll see. But the activity is actually going to be based off of this. It's a really cool way of using the limit definition of the derivative. Understand derivatives in a little bit more geometric way. It's going to be good. All right. Example 5, we're going to finish this video out and call it a day. All right, limit definition of the derivative. We're looking for f prime of x, and that is going to be the limit as delta x goes to 0 of this function evaluated at x plus a little bit more x, and then we're going to subtract off f of x, and we're going to divide by some little difference in x values. We plug things in so that we have the square root of x plus delta x minus square root of x all over delta x. Again, notice that we would be in a situation where we would have 0 over 0 if we tried to plug in 0 for delta x at this point. So we're in a situation where we have the square root thing on the top of the fraction, and we know the algebra trick to use this. We're going to use a conjugate. So we multiply through by the square root of x plus delta x plus the square root of x. And we do that on top and bottom because we don't want to change the value of this fraction. We just want to kind of change its form. All right. So it's all coming together now. We've actually got something where we're using that conjugate thing. Let's do the multiplication through. On top, we'll just have x plus delta x. The middle terms will cancel out, and then we'll have minus x at the end. And on bottom, we'll have the whole mess of delta x times the square root stuff. But what does this mean? Well, x and minus x are going to cancel. Then all we'll have left is delta x on top. So the delta x on bottom and the delta x on top will be able to cancel. And what we'll be left with is the limit as delta x goes to 0 of 1 over the square root of x plus delta x plus the square root of x. And we get to plug in 0 for delta x so that we just have 1 over the square root of x plus the square root of x, which is better known as 1 over 2 times the square root of x. And that is our derivative function. And if we use a tangent line thing where we, look at the derivative at a point times x minus that x value plus the y value, we get the equation of a tangent line. And it's tangent to this function that we have. And yeah, for this one, I used the prime notation just to get the derivative, and I guess it looks like that, but really what we're interested now is being able to make a tangent line, and notice this tangent line works. It's great. All right, so on that satisfying note, I'll leave things. I guess it's kind of interesting to note that we get a completely vertical tangent line there, and we'll talk about the specifics of that later, but yeah, we get a function for the derivative, and then using that function for the derivative, we come up with a function for the tangent line. And if you don't understand this part yet, don't worry, we'll be revisiting that. Yeah, stuff is super cool. I feel like you should understand now that your powers have grown. You can now talk about the instantaneous rate of change of pretty much any function that you want. I mean, evaluating this limit definition of the derivative will be difficult for many, many functions. We actually just kind of looked at some of the easier examples. But yeah, take heart that we're not going to use the limit definition of the derivative for the entire class. These steps aren't going to become part of the routine forever, because it's going to be easier just to kind of memorize some of the common functions and their derivatives and not deal with this the entire time. So yeah, expect to look at this video probably right at the beginning of the activity. This is coming from a channel called 3 Blue 1 Brown, a channel that I thoroughly recommend. Oh goodness, Monday.com. Are you kidding me? Sorry. All this stuff here is just for fun, but yeah. 3 Blue 1 Brown. Super cool channel and really cool animations that go along with all of this. It's going to be great. So for the activity, we're going to be practicing limit definition of the derivative, but also looking at this geometric derivation of the derivative. And it's going to be a great time. All right. So I will see you in class tomorrow. Have a good day.